So today we are going to look at limits, but we're going to look at limits that involve x going to 0 of sine of x over x equals 1. We're going to use this fact to solve equations using limits and manipulating what we're taking the limit of to look like this so we can say that it's equal to 1. So this is a formula, and last week you should have watched a video on how to prove this, and it proved it by using the sandwich theorem, or another way they call the sandwich theorem is the squeeze theorem. So we're just going to go in with this fact that this is a true statement. So if we have something, or we can manipulate what we're taking the limit of as x goes to 0 of sine of x over x, this equals 1. It says the limit of the ratio of sine of an angle to an angle as the angle approaches 0 is equal to 1. This is a standard result used as a rule to evaluate limits of a function in which sine is involved. Okay, so let's pull some examples and look at them. And so in this case right here, we have the limit as theta approaches 0 of sine of the square root of 2 times theta all over square root of 2 times theta. So it's telling us if what we're taking the sine, whatever angle we're taking the sine of, the ratio of the sine of the angle and the angle as it approaches 0 is 1. So this is the same. This is going to give us back 1. Okay, that one wasn't too bad. What about if we had the limit as t is approaching 0 of sine of k over t, or sorry, k times t all over t. And we're given that k is equal to some constant. So this isn't quite the same of the angle that we have on top and the angle or what we're dividing by on the bottom. There's a k in front of the t. And so we need to manipulate this so that it's the same thing. And so we're going to use the fact that we can multiply by 1, or a fancy one, rewriting 1, so that we can get what we want. And so in the denominator, we want k times t. And so we can get that by multiplying both the numerator and denominator by k. And so technically, remember, we could pull coefficients out front. So this 1k that is in the numerator, it's like this times, we can rewrite it as sine of kt all over k. And so all we're going to do is we're going to bring our constant, our coefficient in front, and say this is the same thing as k times the limit as t goes to 0 of sine of kt. Oops, I've dropped my t. It should be down here too, from over here. All over k times t. So I call what we're taking the trig function, that's not always an angle, it could be a real number. So I call what that is the argument. So if the argument of what we're taking the trig function of is the same as what we're dividing by, and that's a sine of it. This is equal to, well, this piece right here is equal to 1, right? And times the k in front. So we have k times 1. Which is k. What if, let's go back up here for a second. We had seen that the limit then as x goes to 0 of sine of x all over x equals 1. What if it had been a little different? What if we had had the limit as x goes to 0 of x all over sine of x? So it's the reciprocal. What do you think we would get back, and how could we show that? We want to use this fact to solve the limit as x goes to 0 of x over sine x. So a way we can rewrite a reciprocal is 1 over what we were looking at. So we can manipulate this. And so, let's see. So this is the same thing as 1 over the reciprocal of this, which is sine x over x. You know, guys all agree with that? So if I have 1 divided by sine x over x, division tells me to multiply by the reciprocal.
Reciprocal.
Yeah. So we get the same thing we have up here. Now we can use those properties of limits where we're looking at the limit of the numerator, where we know the limit as x goes to 0 of this numerator of 1, that's just equal to 1 because it's a constant. All over, then if I look at the limit as x goes to 0 of my denominator, well, by this rule, sine x over x as x goes to 0, that's 1. And so 1 over 1 gives us back 1. So which makes sense, right? This is telling me that the limit of the numerator as x goes to 0 and the limit of the denominator as x goes to 0, they're going to the same value in order to get back 1 other than 0. Okay, so I'm okay now at that point. If you see the reciprocal of what we were just looking at, limit as x approaches 0 of x over sine of x, or if you are able to manipulate it to look like that, you can just say that that's 1 without showing that step of 1 over the reciprocal and doing it that way. So right here is the graph of y equals sine x all over x. And if you look at it, and we're looking at the limit as we go to 0, as we get closer and closer to 0, both on the left and the right, we're getting closer and closer to that y value of 1. But notice it doesn't affect it. If I change my angle, let's maybe say it's sine of 2x over 2x. That limit, as I'm coming in from the left and the right, I'm getting back 1. So I can, any angle I put in here, or a real number I put in there, as long as I'm dividing by that, it's always going to come back 1. I want you guys to be careful though, because there's a difference between sine of x divided by x, and I'll write this out in a second, but let me just write it in here, and sine of if I took 1 divided by x. So notice in here, that's looks like it's like scribbled. It's pretty solid in here, but between as I get closer and closer to 1. So what's happened here is that this is oscillating back and forth really, really fast. And so it doesn't matter where you get closer and closer to one, there's no, or sorry, closer and closer to zero on the left and right. There's no one particular value that it is approaching. So actually in this case, this is where it's undefined. Okay. So right now we're just, again, using that fact that if we have some function or sine of something all divided by that something, as the limit as x approaches zero, we're always going to get back one. And so just like we like to manipulate our expressions or functions so that it helps us solve or get to what we're looking to solve, like multiplying by a fancy one or multiplying by that fancy one using the conjugate to get rid of radicals, we're going to be manipulating things to look like this so we can use that rule. So pulling another example. You write it out and then I'll start the video again. So our next example, I have the limit as x goes to 0 of tangent of 2x, and then that's all over x. And I was just going through really quick, recalling that we can rewrite tangent of theta as the same thing as sine theta over cosine theta. So we want to, again, use the fact that that limit as x goes to 0 of sine x over x equals 0. Sorry, equals 1. And so since we can rewrite this tangent has the trig function sine in it, we're going to do that. And so we're going to use that fact and rewrite this limit. So we have the limit as x goes to 0 of sine of 2x all over cosine of 2x all divided by x. While I was writing that, I kind of thought to myself, really what you should do before you even jump into this is do that direct substitution. But if we did the direct substitution and we plugged in 0, wherever we saw an x in here, we would get tangent of 2 times 0, which is tangent of 0, all over 0. Well, tangent of 0, if you plug it in to be sine over cosine, sine of 0 is 0, cosine of 0 is 1, 0 over 1 is 0. So this is 0 over 0. This is our indeterminate form. And that was the form that didn't tell us anything about our limit, and we had to go back and manipulate. But sometimes, right, it's so easy, you plug in and it comes out really nicely. So that really is the first thing that you want to do. Okay, so that didn't work. And so now we're going back and we're manipulating it so we can use this fact. So remember, this is just like a fraction divided by a fraction. So let's just rewrite this as a single fraction. So I have sine of 2x all over cosine of 2x times the reciprocal of x over 1. And the reciprocal of x over 1 is 1 over x. So I'm almost there. I see this sine x and I can manipulate it. I sine the 2x over x. And so I just kind of want to make it. So I can rewrite this a little bit. This is 1 over cosine of 2x. All times sine of 2x over x. So I just need that 2 down there in that denominator. So we're going to use the fact again of multiplying by a fancy one. And let's make that fancy one. We want a 2 down in here. So if I put a 2 down in there, I need to put a 2 in the numerator. So let's use our rules. So if we rewrite this, limit as x goes to 0, I could technically, I don't need this 2 out here. I can leave it out there or like there, I can put it in front. So the limit of the first function 1 over cosine of 2x times sine of 2x all over. I'm just going to put this 2 in front of this x, 2x. So we have the 2 in front and now take the limit of each function. Cosine, recall, of 0 is equal to 1. So I have 1 over cosine of 2 times 0, or cosine of 0. So I have 1 over 1 times, and the sine of 2x all over 2x using that property is 1. And so when we look at this limit here, as x is going to 0, we get back 2 times 1 times 1, which is 2. So just was a quick question about cosine, this piece, why it was 1, I believe. And so we were going in and doing direct substitution once we had manipulated it, and we plugged in 0 wherever we saw an x. And then we're using the fact in this case that I have in the denominator cosine of 2 times 0, and 2 times 0 is 0. So cosine of 0 is equal to 1. And so we're just putting the 1 down in the denominator. We have that 1 up in the numerator. And so that just gives us back 1 for that piece. Okay, so another question was, why did this 2 over here, when we multiplied by 1, stay down here in the denominator where we pulled the 2 from the numerator out front in here? And so the reason is because we're trying to manipulate it so that whatever we're taking the sign of is what we're dividing by. And so we technically didn't have to bring this 2 out front. We could have kept it, over here. I could have put it on top of this numerator, but I just wanted that one piece to look identical to sine of something divided by that same something is 1, if we're taking the limit as x goes to 0. And so that's why I just left the 2 down in the denominator. And basically these are all, we can think of them all as separate functions. 2 is a function, 1 over cosine of 2x is a function, sine of 2x over 2x is a function. And when we're taking limits of a function times a function times a function, we can look at the limit of each piece and kind of break it down that way. I'm not really doing that anymore, but that's technically what we're doing when we do direct substitution or we use rules like this that we know hold true. Okay, so the next example, we have a limit as x goes to 0 of x squared minus x plus sine x, all in the numerator. And then we divide by 2x. And again, we want to use the rule, if we can, that the limit as x goes to 0 of sine x over x is 1. So we can break this down. I noticed that we're dividing by a monomial, one term. So we could break this down as dividing each term in our numerator by that 2x. And so if we did that, right, this would be x squared over 2x minus x over 2x plus sine x over 2x. So we can use our rules of exponents, right? So the limit as x goes to 0. So x squared divided by 2 over x. So we can cancel an x in the numerator with the 1 in the denominator. So we're left with 1x in the numerator over 2. Minus, so x over 2x's, both of the x's cancel, and I'm left with 1/2 plus sine of x all over. I think it will help us if we rewrite this a little bit. Oops. Funny, I was looking for my pens to get the red pen. I've been teaching them in classroom again, so I've been using color pens. So anyways, so let's pull that 2 right here, this 2 out front of that sine x. And I can rewrite it as a 1/2 in front. Because doing that now, this one piece sine x over x, I can use the fact that that's 1. So we're going to go through and we're going to do direct substitution. So wherever we see an x, we're going to plug in 0, except for that last piece. We know that that's 1. If you plug in 0, well, 0 over 2 minus, notice there's no x for this term 1/2, so just rewrite 1/2 plus this 1/2 and sine of x all over x as x goes to 0. This is equal to 1. Zero over number, if that one's okay, that's 0. So we have 0 minus 1/2 plus 1/2, which is 0. So the next example, we have the limit as x approaches 0 of 1 minus cosine of 3x all over 2x. And again, we want to use that rule that we've been using all along in this lecture. The problem is, notice that there's no sign in this function. And so you kind of want to manipulate this so that we can get this sine of x over x. And so you got to kind of think back to trigonometry and some of those really huge identities that we use a lot. So one of the identities that you guys used was if you had sine squared theta plus cosine squared theta, this was equal to 1. So this was one of your Pythagorean identities, trigonometric identities. So I noticed that if I can manipulate this, notice that sine squared theta, if I isolated that and got it by itself, is the same thing as 1 minus cosine squared theta. That's a difference of squares. So notice up here in my numerator, I can make that look like a difference of squares, right? By multiplying by the conjugate. So if I multiply by the conjugate, though, I need to multiply by the conjugate of the numerator and the denominator. And again, I probably should have stressed this. We should have started by plugging in 0 wherever we saw an x. But if we had done that, we would have gotten 0 over 0. And then so the next part is trying to manipulate it. Okay, so let's multiply by, again, a fancy one, but this time we're going to multiply by the conjugate of this numerator. So let's multiply it by 1 plus cosine of 3x. So 1 plus cosine of 3x. So I'm just going to distribute in the numerator and not in the denominator. I'm going to leave them as factors in the denominator. But really, we don't need to distribute. We should know that if we have a minus b times a plus b, we can just square the first minus the square of the second. And we're going to use this fact over and over again, so we can just do that without having to think about FOILing that out. So 1 quantity squared is 1 minus cosine 3x times cosine 3x. That's cosine. We tend to write it with a square here, cosine squared of 3x. But again, if you have some trig function raised to some power, so let's say n of x, this is the same thing as saying you're taking that trig function, in this case cosine of x, and raising it to the nth. Okay. And so this is all over this 2x all times this 1 plus cosine of 3x. So this is where we're going to use this fact. And so we can rewrite our numerator as sine squared. But instead of theta, we're going to write it as 3x. All over 2x all times 1 plus cosine of 3x. We always bring down our limit until we take that limit. So that's a thing that students don't like to bring it down all the time and leave it off. But mathematically, you got to get into writing things mathematically correct. So bring it down each time when we're doing that. We're almost there. We have the square in here, so we might want to rewrite it. And let's see if we get 0 over 0. If we do, we're gonna have to go back and manipulate this a little more. So I kind of want to manipulate this a little bit by rewriting it. So how about, remember I just said, so the sine of square root of 3x, another way to write this is, how about just sine of 3x times sine of 3x? So I have sine of 3x all over, let's put it over this 2x, times, I need another sine of 3x, all over 1 plus cosine of 3x. So that first fraction almost looks identical. The only problem is I have a 2 down there in that denominator and not a 3. So, and I don't really want that 2 right there. So another thing I can think of is pull out a 1/2. So almost there, we want that to be a 3 in front of that x. And that first one out, second parentheses. So if I put a 3 in front of this x, I basically have to multiply that numerator by 3. So I could technically put that 3 up here. So all I was doing was multiplying by a 1 and just kind of rewriting the single fraction as a product of multiple fractions.
Wait, Miss Knopfsinger, where did the 2 come from?
The 2 came from this 2 right here. I didn't want it to be a 2 because this was a 3 up here. And so I just pulled that 2 out front.
Okay, makes
like
sense.
1/2, yeah. And so now if I look at the limit of each product, so the limit of a constant 3/2 is just 3/2. If I look at the limit of sine of 3x over 3x as x approaches 0, we know that that one is 1. We just manipulated that, times So as long as we don't get 0 over 0, we're good. Sine of 3 times 0, well, that's sine of 0. Sine of 0 is 0. All over 1 plus cosine of 0 is 1. So cosine of this would be 1 plus 1 on the denominator. So we technically have 3/2, right, times 1, but 0 over 2 is 0. So we have a product there with 0 in it, and so we get back 0. So again, if we graph this and go and look at this, and we look at the limit on the graph as x is approaching 0 on the right and 0 on the left of our x values, the y value we should be seeing is it's approaching 0. Let me just. So like I just said, graphing the function, and I just graphed it on Desmos, we should see, and we just found doing algebraically and using that manipulations, that as the limit as x is approaching 0 on the left-hand side, our y value is approaching 0. And if I come in on the graph as x is approaching 0 on the right-hand side, that y value I'm approaching is also 0. And because of that, then the limit itself is equal to 0, because left and right are the same. So now we're looking at the limit as theta approaches 0 of sine theta times cotangent of 2 theta. So on these, probably helpful if you have any tangent of theta, cotangent of theta, secant of theta, cosecant of theta, is to convert it in terms of sine and cosine. And so recall that cotangent of some value x, we can rewrite this. This is the same thing as cosine of x all over sine of x. The reciprocal of tangent theta. And so let's go in and rewrite this limit. Actually, before I do that, actually, I'm going to rewrite it still. So limit as theta goes to 0 of sine theta all times. So cotangent of 2 theta is the same thing again as sine of 2 theta all over cosine of, actually it's not. I lied. It's cosine on top. Cosine of 2 theta all over sine of 2 theta. Unfortunately, our angles are not the same, so I don't know that those are the same values for sine of theta and sine of 2 theta. If I do put in 0 though, sine of 0 is 0. All over the denominator, I would get sine of 2 times 0. So sine of 0 is 0. So I get the 0 over 0, that indeterminate form. So again, I'm trying to manipulate this to look like what I want. And remember at the beginning of class, we said that if we took the reciprocal and instead we wrote it as x over sine x, this we saw was still equal to 1. And so let's use both of these facts. The one we started with is equal to 1, and then the reciprocal of that also gave us 1. So if we do that, then I know that basically underneath this cosine of theta, I want 1 theta. So I can do that, right? I can multiply by a fancy 1 of theta over theta. And then this sine of 2 theta, so I don't know if that would help you if I rewrote it. So this is theta goes to 0. Let's keep that theta right here. All times the sine of theta all over theta, which we wanted. All times, let's just rewrite this as cosine of 2 theta. If you want to, you can put that over 1, but we don't need the 1. And this is 1 times sine of 2 theta. So we're trying to get the same argument of this sign in the numerator. So I know I need a 2 theta up there, but hey, look at, we already put a theta up here. So can't we just move it over here? The other thing is, okay, now I have my theta there, but I want it to be 2 theta, right? And so I can multiply both the top and the bottom by a 2. So if you think about it, I'm just going to think of this 2 as multiplying by a half. So we can rewrite this again. Limit as theta goes to 0. We have our sine of theta over theta times our cosine of 2 theta over 1 times our 2 theta all over sine 2 theta times 1/2. So now we can use our rules and we can do our direct substitution. And so if we look at sine theta over theta, as theta goes to 0, this piece, I'm just going to write an arrow. This piece is going to 1. Maybe I should have done that on the bottom. So as this goes to 0, this piece goes to 1. If I plug in 0 here for this piece, cosine of 0, that's also 1. So 1 over 1 is 1. So that piece goes to 1. You saw that again, as long as our argument of the sign that we're taking is the same that we're dividing by, or in this case, like this also went to 1. And a limit of a constant was always just that constant. And so this piece went to 1/2. And so now we didn't get the form, an indeterminate form, like we would have originally gotten plugging in that 0. You have 1 times 1 times 1 times 1/2, which is 1/2. Okay, so we finally finished this 2.4 section in the book. And so tomorrow's class, I'm going to go backwards and I'm going to go back to 2.3, which is the formal definition of a limit and showing why a limit exists instead of saying it's approximately or it's getting closer and closer and closer. So in more mathematical terms, we're going to show why we can prove limits by the precise definition.